Number two. I usually like to put a study guide, but I didn't make one because I was so busy preparing the rankings and that kind of a thing. I apologize. I'll throw one together and get it up here. But here's the main thing for it. I don't think we've covered that much since the last test. How do you feel about that?
Same.
In general, the main thing we've covered since the last test is genetic algorithms. And so I will ask you questions about what is a genetic algorithm, how do they work. I'll probably have you do an example like, here's two chromosomes, please do crossover and produce a child chromosome, something like that. I might ask you a question about how would interpolation differ from crossover? How would extrapolation differ from crossover? Does that make sense? In fact, I'm talking a little too fast here. Let's slow down. And how do you do crossover?
What type of crossover? There's like 1,000 different ways to do crossover.
There are. So here's the standard crossover question. Here's chromosome number 1. Here's chromosome number 2. Suppose they have a baby. What does the baby look like? And if you say G-A-T-A-C-A-T, T-A-C-T-A-C-C, you are correct. If you say G-A-T-A, and then you switch C-T-A-T-A-C-T-A-C-C, you are also correct. The difference is, in this one, we switched right there, and in this one, we switched right there. So this is what's called single point crossover, and if I ask you to do single point crossover, that's what you do. You pick a point, and then at that point, you cross over. And the whole purpose of it is it makes a new gene, and that's what it does. Any questions on that? Okay. A common implementation with single point crossover is to say that every pair gives birth to twins. And that way, if this is one pair, if Gattacat and Tac-Tac is one twin, then Catacta and Actatac is the other twin. And that way, they're always the exact opposite twins. There's no real good reason to do that, it's just something to do. Okay? What is double point crossover? Where you take 2 points. So now the child would be Catac, Attacked, Tact, or something like that. And that's one way to genetically recombine children. Okay, so a good question to ask on top of this is, why do that? What are we trying to do in a genetic algorithm?
Emulate real life.
Yeah, so we're trying to be biologically inspired, and presumably that's sort of like how genes recombine. Now, I don't know specific details about how genes work, so I'm not going to get all biological on you. And I don't care if you believe this is how life originated, but I do care about it in the sense of optimization techniques. So you should know why crossover is good for optimization. Why is crossover good for optimization?
It tries new things.
Yeah, it explores the space pretty well. What's an alternative to crossover for replenishing the population?
Something more random chromosomes.
I want to say the alternative is probably something like interpolation. Suppose your genome looks like this: 0.1, 2.3, 4.8, 0, and the other one is 0.2, 9, 8.8, and 10. Another way to generate an offspring genome would be or offspring chromosome would be to average those together. So you'd have 0.15, 2.6, 6.8, and 5.05. something like that. An improvement to that would be weighted averaging, right? You could do, pick a random value between 0 and 1 and weight them based on the 2 chromosomes. What would happen if you pick a weighting that's not between 0 and 1?
Extrapolation.
That's extrapolation rather than interpolation. Okay, so if we were to do this graphically, suppose red is the father and blue is the mother and green is the child. If I were to do single point crossover, where would the child go? Either here or there, right? Now, in reality, it wouldn't be 2 dimensions, it would probably be 100 dimensions, because you probably have a 100-dimensional gene, so it would be one of the corners in 100-dimensional space. How many corners are there in 100-dimensional space?
A lot. 100 to the 100 color.
So, in a 2-dimensional box, there are 4 corners. In a 3-dimensional box, there are now 8 corners.
2 to the third.
In a 4-dimensional box, surely you guys have all sat around doing this at one point, right? Drawing n-dimensional boxes, hoping your mind could somehow fathom what it does. And how many corners are there in this 4-dimensional box?
16? Just a guess.
16. And how many are there in a 5-dimensional box?
2 to the guess.
32. So how many are there in a 100-dimensional box?
2 to 100.
2 to the 100th power. There are a darn lot of corners in a big box. And that's kind of the main intuition behind why single point crossover is such a good thing. You're essentially exploring one of the corners, and there are a lot of corners. And so it's really good at exploring the space. If you do interpolation, you're picking one of the points between here and there. And if you do extrapolation, maybe you're going a little further. But you see how that doesn't explore very well? Imagine a big space. It's kind of assuming that these parents are really good and choosing something very much like them. Whereas crossover is very exploratory. It creates a whole lot of diversity. So I'll try to ask some questions to see if you get the general intuition behind why it's a good idea to do crossover and what you're trying to accomplish and something like that. That make sense? Okay. The other nice thing about crossover is it works with discrete values. You can do it with Gattaca, or if you have categorical values, whereas extrapolation and interpolation only work if you have continuous values. Okay. So on that topic, what are the main components you need in a genetic algorithm to make it work?
Genes.
You need genes of some type.
Or like things you can make into genes.
Okay. Yeah, you need some way of encoding your problem into a vector of numbers, right? What do you have to do in a genetic algorithm?
Mutate.
Promote diversity.
Yeah. So if I were to ask that question, what are the things that a genetic algorithm has to do? I'm gonna want you to give an answer like, do something to promote diversity, and do something to some kind of selection. Essentially, if you do both of these things, it should work in general. And these are pretty vague concepts, right? How many ways are there to promote diversity? 11. And what is number 6? Mutation. Okay.
I'm not sure if joking.
I shouldn't joke because somebody in this room is probably from a country where they don't joke like that and is just lost right now, and I'm sorry. Okay, I lived in China for a couple of years, and I had a friend who one day just decided to walk into a Domino's Pizza. And he just walks into the counter and he says, "Hi, I'd like this pizza delivered." And they said, "Sorry, we're not available for delivery right now." He said, "Oh, that's okay." He hops over the counter and pulls the keys off of the rack and starts walking off like he's going to go deliver it to himself. And he says, "I'll just borrow your bike and I'll take it home and deliver it to myself." Because they had these motorbike delivery vehicles. And they couldn't figure out that he was trying to be sarcastic. He had this weird sarcasm way of being. And because there was the whole cultural diversity, they just didn't understand, and they started talking among themselves about how these Americans are so crazy. They just walk in and grab the keys off of the delivery vehicles and start driving pizzas around, and you just don't do that in China. And so they started talking to him about how that might be acceptable in America, but you just don't go take the keys to a random delivery vehicle over here. And he started laughing about it, and it just wasn't very funny, actually. But it's a funny story. And so that's why I did that. Okay, that was way off topic. Getting back online, genetic algorithms need to promote diversity and do some kind of selection. Okay. So ways of promoting diversity. I'm going to claim there's crossover. There's mutation. What are ways of doing selection? You could do random selection. Would that work in a genetic algorithm?
Luck is on your side.
The whole point of selection is you're supposed to promote survival of the fittest. And if you're promoting survival of the survival of the lucky, I'm just going to say that's not going to work. So there might be a lot of luck in the real world, but there needs to be some kind of pressure for the better ones to survive, or else the real world wouldn't evolve. At least in theory. And in optimization, that's very true. If you do it randomly, you will not. No, that's not true. You might stumble across a great gene.
You wouldn't keep it though. It would disappear after time.
Yeah, if it's a hard problem, you need some kind of pressure towards survival of the fittest. So
Can it adapt to the randomness?
please be familiar with tournament selection. What is tournament selection?
Competition.
That like the one that you created where you put them all together, or like just?
Actually, I think I misled you by doing that. Tournament selection means you randomly pick two from the population and you put them in the cage of death and one emerges.
I feel like that should be called dual selection.
It probably ought to be called dual selection, yeah. Thunderdome selection. The tournament selection means you have two of them to get in a tournament. Man versus bear. Bear whips out the claws, man whips out the gun, bang, bear dies, man lives because man is more fit than bear. Unless man doesn't have a gun, in which case the bear is more fit than the man.
Have you seen The Revenant?
I have not seen The Revenant, no. Is it a good movie?
That's pretty good.
Okay, cool. My wife didn't want to see it, so
Probably shouldn't check.
I'm probably not going to see it anytime soon. All right. What's it called when you do a full tournament where every pair battles against everything and then you pick the winner?
A selection that takes very long.
Pairwise?
Slow. Yeah, Dr. Gassler's version. There's another type of selection that's well known in genetic algorithms, which is called fitness proportionate selection. The idea of fitness proportionate selection is you go rank how good every gene in your population is, and in proportion to how good it is, they survive. Or in proportion to how bad they are, they die.
How would you know how good the genes are, though, without doing something to test that?
So that's a good question. There are many problems for which you can't do that. So suppose your gene is controlling a ball to play sumo billiards. In that case, you get a gene, how good is it? Really hard to tell. Suppose instead you're trying to evolve the optimal antenna for picking up a signal. And there's actually a reason I bring up that example. If you look up on Wikipedia, there's an antenna that was evolved by a genetic algorithm. And it turns out this genetic algorithm was used on the NASA ST-5 spacecraft. This complicated shape was found by an evolutionary computer designed to create the best radiation pattern. It's known as an evolved antenna. So, in this case, suppose you're evolving an antenna. How do you tell how fit a gene is? Yeah, basically what they did is for each gene, they either simulated or maybe actually physically printed an antenna and tested it and tested how good its radiation properties were and scored it somehow. So if you've got a scoring mechanism, then fitness proportionate selection, where was I? Here we go. If you have a scoring mechanism, fitness proportionate selection can be used. Whether you do or not, tournament selection is almost always applicable. I like tournament selection better because, well, let me ask you, how would the properties of these two differ?
Aren't they kind of the same?
Yeah, that's kind of what
And then you're ranking it, right? One does better than another one.
They are kind of the same, but there's a significant difference. Suppose I'm going to draw what I'll call a landscape. Suppose one of them is up here and one of them is down here, and you do a tournament. Which one's most likely to win? This one, because he wins the tournament because this one's better than that one. Now suppose that one of them's right there and one of them's right there. Who's probably going to win the tournament? One on this one, because it's still better. So with tournament selection, there's the one that's better usually wins. With fitness proportionate selection, it's in proportion to how much better they are. So it's almost 50-50 as to which one would be picked here. But with tournament selection, it would definitely be the lower of the two. And by definitely, I mean probably. So we'll talk about that in just a minute. What I'm going to claim is if you use tournament selection, it's going to go faster. It's going to evolve at the same speed, whether you're making a lot of progress or a little progress. Meaning these balls are going to move horizontally quickly, even when it plateaus out. Whereas with fitness proportionate selection, they're going to slow down when it starts to level out. You see why? Okay. There's a difference, and sometimes it makes a big difference, sometimes it doesn't, and depending on the problem, one can be much better than the other. So there's that.
We're assuming so that for the tournament selection, the loser always dies. It's
Well,
not, or is,
actually, the answer is no. The loser should not always die in tournament selection. Why not?
in case they have
Could be the second best.
So it's actually up to you, and you can do that if you want, but it's the general wisdom of genetic algorithms is sometimes make the loser win. Can anybody give me an example for why?
Local maximums.
Yeah. Suppose your search space looks like this. Where the vertical axis is badness. Okay, let's do it this way. Do goodness. So this is how good the genes are. And suppose your population is distributed like this. One here, one here, one here, and one there. Now suppose you keep doing tournament selection, what's going to happen?
they'll converge.
They'll all start moving closer to this way because that's the ones that keep winning. And eventually you're going to discover that, hey, the very best place is right there. But in fact, the very best place is obviously right here. Do you see why losing sometimes is good? Because if the loser wins, then what happens is there's some amount of pressure to kind of explore. And if it explores, then all of a sudden this might happen. And then when this guy tournaments against this guy, that one will probably win, although maybe not. And if it doesn't, we'll lose one. But there's still other members of the population that'll sort of help pull the pressure over. And so in the end, you end up here because you let the loser win. Does that make sense? So on a test, I'll probably ask some question about local optima. This is what's called a local optimum, meaning it's optimal locally. It's better than any place near it, but it's not the best place. So this is what's called a global optimum. It's the best place in the entire globe, where globe is used to substitute for the space of all possible genomes. Okay. So the general wisdom is maybe make the winner of the tournament prevail 80% of the time, maybe make the loser of the tournament prevail 20% of the time, something like that. Now, what if you happen to know that your search space looked like this? Except for that spot right there. This is what's called a convex optimization surface, and there's no local optima. Now there's not. Okay. Would it be to your advantage to ever let the loser win in this type of a search space? I'm going to claim the answer is no, because basically if any gene is better, it's closer to the global optimum, right? You see that? So the simpler, the more convex your optimization surface is, the more you want your winner of the tournament to always prevail. And the more complex the surface is, the more you may want the loser to sometimes prevail because you want to explore. Okay.
Is there a scenario where you would know which surface you're working with?
Usually no. In general, if you're using a genetic algorithm, it is assumed it's some crazy complex problem. Otherwise, why are you using a genetic algorithm? There are much better algorithms for convex optimization. So that's why, in general, you never want to say that the winner of the tournament always prevails. What would happen if you let the winner of the tournament prevail, say, 50% of the time?
You may not get one.
Now you're just doing random selection, right? So it better be more than 50%. And should be less than what? 100%? And what's between there, what should it be? I don't know. Yeah, so here's a question. Suppose you have these parameters that you need to tune. How can you tune your parameters? If only we knew some technique for optimizing values for an arbitrary problem, right? How would you do that? Or how might you do that with a genetic algorithm?
Encode them on the chromosome is another.
Okay, there you go. Yeah. So you could actually have a genetic algorithm within your genetic algorithm if you want. But that gets complicated. Why? You're already running a genetic algorithm. So if you encode parameters in your chromosome, then the ones that survive presumably have good parameters, right? So you can use those to guide how your genetic algorithm works. And if you do that, then the genetic algorithm tunes itself. And so in theory, this thing should evolve to become a really great optimization algorithm. That's kind of elegant, I think. Okay. So anything pertaining to intuition of genetic algorithm is pretty much fair game. And on top of that, basically I'm going to repeat a whole bunch of the tests from last time. Why? Because I think repeating tests makes you go back and understand what you did wrong. And I think that's a good thing. So study what we did last time. I think we should also go over the study review sheet from last time and make sure that you get everything we've covered there. And other thing I want to point out is simply that the lectures are online. Is anybody not aware that you can go here to see the lectures? Well, here they are. So there's a bunch of stuff to go over. Don't go watch them all. They're very boring. That's what school's for. Being boring.
Some of the early OGG files have like a staticky thing in the background, like all the time.
Yep.
It's a little.
I'm sorry. I don't know what that is. Yeah, basically I'm still figuring out my recording system, and sorry about that. If somebody wants to go through and notate when new topics begin, that would be really helpful for all of us. Okay.
So on the test, are we gonna see a return of the wall market problem?
Ah.
Oh, God.
So let's go back and take a look at that. We actually went over the wall market problem. I'll say I have not made the test yet, so I can't even answer the question because I don't know. I do feel that you should understand utility theory because we've gone over it. That problem was a pain to grade. I would like to make one that would be easier to grade. But I also want you to learn from your mistakes, so I want to say that one's fair game. Plus, I did it for you. It's right here in the lectures. Let's find it.
Are you sure that wasn't one of the ones that was lost?
Question 3, 540.
Let's find out.
Have less than 1 in 10 million chance of being isolated every place. So if you
No, it's right here. There's the answer to the wall market one. Send or not send.
Give this tree structure
13 out of 67. 54 out of 67. X and 1 minus X. I would go back and look at this question and make sure you get that answer. Just do that, and that way if I put it on, no harm done. Okay.
Now, if you put it back on, will it be the exact same problem, or how much will you change if you were to?
Well, so here's the deal. I covered so little content that if I give you that much information, I've got no leeway as far as testing you. So at least give me the courtesy of being able to change some things. I may or may not adjust the questions. But the topics are going to be a whole lot of what we had on the previous test, plus genetic algorithms. Okay, let's look at what else there is here. So I do still expect you to understand uniform cost search, A-star search, these types of things. How to represent things in high-dimensional space. Understand genetic algorithms in general. And I can't think of a darn question to ask on Torch the Flag, can you? I won't ask you who won. But you should know what a software agent is. What's a reflex agent?
One program.
Yeah, reflex agent is one where you just hard code your own human logic, and AI agent is one that does some kind of loop that crunches numbers for a while in order to improve an answer. There you go on that. That's all I have to say as far as preparing for the test. Any questions?
Well, since we're only going, like, the only new material is genetic algorithms, can we just have a quiz over genetic algorithms and then talk about random forest the rest of the class?
Using class time to do random forest is a good idea. I don't know, somebody might want the whole time. I'm going to give you the whole time period to take the test just in case. It will, I'm going to make it a little smaller than the last test. The average score on the last test, I think, was in the 70s. I think we can do better than that, and so I'm going to repeat myself a lot because I want you to learn from your past mistakes. So I'm expecting the average score to be much higher this time, and that'll bring the grades up to where I think they should be in the class. So yeah, it'll be a full test with a lot of repeat, not just a quiz. Okay.
Can I say something?
Yes, please.
For exam 1, I made a Google Doc that we all just kind of edited and added notes. I'm going to do this again for this exam, so just look on the forums if you're interested, and I'll post a thread and a link to the new folder.
Okay, I'll try to add a list of topics here, but it'll be pretty short because I basically just went over everything I can think of right now. Try to make sure you get the intuition behind these algorithms. If you've got that, I guess I'm pretty happy. Okay, so the next thing is I want to start talking about the decision tree assignment. Can we start talking about that now? Okay. So you saw that I moved it back. Is anybody really upset that it's not due right away?
No,
We're okay with this. Okay. If somebody's really mad because you worked really hard, come talk to me. I'll try to compensate somehow. But okay, Random Forest. Download this starter kit. How many of you have looked at that? Is it bad? Easy to understand?
One thing that would be kind of helpful would be, I felt kind of dumb for missing this, but your node class, the abstract node class, and your leaf nodes and your interior nodes.
Okay.
The leaf and the interior nodes don't actually extend the abstract class, which gives me an extra. I was like, oh no, but it has to work. But it wouldn't work because I didn't realize they didn't actually extend them. I felt kind of silly.
Thank you.
Wait, what? I'm not sure what you.
I'm going to fix that right now.
It's like, I know I remember
Extends node. Leaf node. Extends node.
And technically, the node has to be abstract. It has to be declared abstract to have an abstract method.
Okay. I should actually compile stuff before I offer it as helpful. I never uploaded it. Okay.
That's the point.
Okay. Yes, it does have to extend the node class in order to work. I apologize for that. By the way, I hope this code wasn't that helpful. Right? I mean, I'm not saying I don't want to be helpful. I'm saying that, you know, you should be able to understand that a tree is made up of nodes, and nodes have leaves and interior nodes and that kind of thing. Okay. I wished I had taken a little bit of time to go over how to code in Java before the previous assignment. It would have saved me a lot of effort. Let me do that really quick. Just because.
Are we getting a paradigms review?
Just a real quick one. I'm not going to go over all the paradigms, but
Just the important parts?
no, just the things that burned me on this on the tournament assignment. Okay, so
How do you get to this class without using Java, though?
what's that?
How do you get to this class without using Java, though?
Well, using it's one thing. Knowing what I'm thinking is an entirely different thing. Okay, so what do I want to look at? I don't want to critique anybody's code. Okay, let's do one that we know is awesome. Who was the winner?
You can do mine, Mr. Anderson.
Mr. Anderson. Okay. So, almost everybody had classes, and a lot of them. Okay, let's go back to previous instructions. This is kind of after the fact, but if you look down here, please keep all the code for your agent in a single file. How do you write a whole bunch of classes in a single file, or can you in Java? You can. Here's how you do it. You just put a bunch of classes in a single file. It actually works. Unless they're public. If they're public, Java forces upon you to put it in a file with the same name as the class. In this assignment, you didn't actually need them to be public because I just rebuilt it. So that shouldn't have affected you. Now, the next thing is how do you make sure your class doesn't collide? When I tried to compile, the first thing that happened is there were about 10 implementations that had a class named class MyState in it. Now that's my own fault for that name because I gave you a MyState class and then I made you do uniform cost search. But how do I resolve that?
Put it
So
interior.
if I call it static and then put it inside of another class, now I have a class within a class. Did you know you could do that?
Nested classes.
You can, it's a weird Java thing. But the thing is this class is now, the actual name of that class is now Mr. Anderson.MyState. And it's a separate class. But because everything that accesses it is in Mr. Anderson, the compiler adds that automatically. So I took all your classes and painstakingly moved them into your classes. I don't think I did that one. I think you already stuck it in there. But if you didn't, I moved them in there and tried to get it to compile. So there's that. You can stick a class in Java, and it's a thing. What happens if you don't have static there? Then it's actually weird. It's not an error. It's a class that has a dependency on the outer class's object. And you need an object to make this class. So this is what's called a closure, and it contains a reference to whatever object was used to instantiate the object of the inner class. Basically, it's a complicated mess that you should never use. Always use the word static when you use an inner class. Unless you know what you're doing, in which case, sort of a complicated mess. There are actually 4 types of inner classes, and I can't remember what the other 2 are. But you never want to use them. Always use static inner classes. Okay. The nice thing about this is now if you have a MyState class and it's inside of Mr. Anderson, now everyone can have MyState classes. They don't clash with each other. So that would have saved me time. Okay. Another thing that a lot of people did, and this one drives me nuts, is your code says at the top, package, some package. What does this mean? That means you use NetBeans. NetBeans automatically adds this line to every file you touch, and it makes it so people don't know how to build their code from the command line, and they get trapped inside of NetBeans. A package is actually a namespace thing. It's a way it makes your class go inside of a place where it won't clash with other classes of the same name. And you have to build it with a special command, and I don't know what it is, so I just always remove that, and then it builds. So there's that. What else? Anybody else have any big Java problems? That's all that's coming to my mind at the moment. I'll leave it at that. Okay. Looking back to the assignments. I'm sort of afraid if I start dumping the assignment on you right now, when your heads are full of the midterm, that's going to be a bad thing. Do you want to adjourn, or do you want to keep digging into this assignment?
I think it would be better to do a little bit now, a little bit later, than to try to do it all later.
That was a good argument. Nobody else agrees.
Can we see the best agent versus the worst agent?
All right, let's play with agents. We'll come. I'll talk about random forest after the midterm, then we can focus on it and do it right.
Well, only 2 days to do it then.
If you want to go, you can. Otherwise, let's stick around and play with watch tournaments.
The name of the agent appears on the map.
Oh, you probably shouldn't do that then.
It does. I won't pick the worst. Let's pick a few. Let's just do some really good ones that I know play a good game.
Try mine. I wasn't in the top 20, I guess.
Okay.